Hey guys, in this video, which is the third video for our central limit theorem series, we're going to be using central limit theorem here kind of now out in the wild. So we saw central limit theorem for means, we saw central limit theorem for sums. Now here we're just going to kind of try to figure out, okay, a generalized central limit theorem, and given a general distribution and kind of a general problem, when do we use it, how do we use it, and kind of what do we do? So in general, it is important for you to understand when you use the central limit theorem. If you are being asked to find the probability of the mean, so if you're being asked to find probability of means, use central limit theorem for means. So for means, remember, mu of x goes to, so your original mean stays the same, okay? Your standard deviation, however, goes to the standard deviation divided by square root of n. Okay, so your new mean for your sample distribution of means is the same. Your new standard deviation is the standard deviation divided by square root of n. So this is for means. Now for sums, if you are being asked to find the probability of a sum or total, use central limit theorem for sums. Now for sums, I'm going to write this better. For sums, the mean goes to, mean goes to mu of x times n, right? And the standard deviation goes to the square root of n times standard deviation. So for sums, mean goes to mean times n, and standard deviation becomes square root of n times standard deviation. But then we get to keep using normal CDF on the calculator kind of the same way. Okay? So, but this note here, if you're being asked to find the probability of an individual value, do not use central limit theorem. Use the distribution of its random variable. In other words, use the original distribution for that. So let's see an example. A study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution. So we have to think back now to all of our uniform distribution stuff. With the lowest stress score equal to 1, okay, so that's our A, and the highest equal to 5. Okay, so there's our B. So this distribution looks like 1, 5. Using a sample of 75 students, okay, that's an N, find the probability that the mean stress score for the 75 students is less than 2. Okay, so since the individual stress scores follow a uniform distribution, X is uniform from 1 to 5, where A is 1, B equals 5, then the mean here, so the original mean is A plus B divided by 2, or 3, so this will also be our mean. The original standard deviation is b minus a squared over 12. So this is straight out of uniform distribution, which is 1.5. So this is mu of x. Here's our original standard deviation. Original mean, original standard deviation. Okay, now what are we going to do with this? So again, original mean, original standard deviation. Okay, so if we're doing the mean stress score, so the distribution of the means, we do lower limit, so right here, upper. 3 is our mean, and our probably the mean square stress score is less than 2. So lower limit is 1, upper limit is 2 because we're in a uniform distribution. Mean is 3 because mean stays the same because we're doing means. Standard deviation, remember, goes to standard deviation divided by square root of n, where n is 75, so that goes here. So we throw all this into the calculator and it looks like we end up getting a 0, which means the probability that x is less than 2 is equal to 0. So here's 2 less than, looks like a big fat 0. In other words, there is no probability that that's going to happen. Okay, same example, different type of question. So stress scores follow uniform distribution. A, B, or sorry, N. So again, our original mu was 3. Our original standard deviation was 5. So our regular mean is going to be this. Our new standard deviation, as we are going to see. So 90th percentile for the mean of 75 scores is about 3.2. This tells us that 90% of the means of 75 stress scores is at most 3.2, and that 10% are at least 3.2. So inverse normal. Here is percentile. So 90th percentile. This was our mean, right? Remember, for means we stay the same. For sums, it's different. Here is our new standard deviation. So plug all this into inverse normal and we get 3.2. Okay, so again, remember, when you're doing the distribution for means, your mean stays the same, but your standard deviation now goes to the standard deviation divided by square root of n. You can still all throw that into the calculator. Find the probability that the total of the 75 stress scores is less than 200. So again, mean of the sum of 75 stress scores is total. So this is a total problem. So total is another word for sums. So we're no longer using the mean, we're using the sums. So this is n. This is our mean. So our new mean for our distribution of our sums, our sample distribution of sums, remember, is n times the mean. So this is now our new mean. So for the sums, 225. The standard deviation, remember, is now square root of n times the old standard deviation. So this original standard deviation divided by square root of n, which is 75. So new standard deviation, new mean, this all goes in the calculator, and this is a less than problem, which means we're doing normal CDF of negative 10 to the 99th. That's your lower. Your upper, less than 200. Your mean now is 225. And your standard deviation is 9.96. So this is what goes in the calculator. So lower, again, upper, new mean, new standard deviation. Why is this different? Because again, we're dealing with sums. So means and sums are different, and you need to recognize the keywords of when to use either one. Okay, so similar problem. The 90th percentile for the total stress score. So total is the keyword for sums. Okay, so we're doing sums again, but we're doing percentile now this time. So the 90th percentile. Okay, so inverse normal, 90th percentile, 0.9. Again, this guy here is n times the mean because we're in sums. Square root of n times the old standard deviation. Throw all this in the inverse normal, get 237.8. This means all the area to the left of 237.8 is 90% of all the area. So in general, you need to figure out, again, when you are using sums, and when you are using sums, the mean transforms to n times the mean. When you are also doing sums, your standard deviation goes to the square root of n times the old standard deviation. New mean, new standard deviation, but inverse normal and normal CDF are used the same. So you need to know whether you're in a sum situation or you're in a mean situation. Let's see, we're not going to go over these guys because it's not necessary for what we are going to do. Okay, but this is. So in the United States, someone is sexually assaulted every 2 minutes on average. So 2 minutes on average, according to a number of U.S. studies. Suppose the standard deviation is 0.5 and the sample size is 100. 2 minutes. There's our mu on average because this tells us. Find the median, the first quartile, and the third quartile for the sample mean time of sexual assaults. So we want to find the median, the first quartile, and the third quartile for the sample mean. Therefore, we are in a mean environment, which means our mu gets to stay exactly the same. Our standard deviation is now going to be the standard deviation divided by square root of n. So keep that in mind. So mu is 2, and it's going to stay 2. Standard deviation is now standard deviation divided by square root of x. So 0.5 divided by 10, because n in this case is third quartile, 0.5 divided by 10. Therefore, 50th percentile is the mean, which is the median, which is all the same. So that's 2. 25th percentile, inverse normal. Sorry, this is also supposed to be 100, because n is 100, not 10. So 25th percentile, inverse normal, 0.25, that's your percentile. 2 is the mean. 0.05 is your standard deviation. 1.97. 75th percentile, so this is first quartile is 25th percentile. Third quartile is 75th percentile. All of this uses inverse normal. 75th percentile, mean, standard deviation, gets you the number. Alright. Let's look for another one. Find the median, the first quartile, and the third quartile for the sum of sample. So for sums, remember, mu of x goes to mu of x times n. So now our new mean is the mean times n. Our new standard deviation is the square root of n times old standard deviation. And then we get to throw it in our calculator like the same. Let me trash all of that. Sums. Alright, so our mean of our sample sums is n times the old mean. So n is 100. Here's the n. Mean was 2. Standard deviation is 0.5. So mean is 100 times n. So n times 2. Sorry. N is 100. Mean is 2. So 200. So 50th percentile, then it would be 200, because the 50th percentile is also the same as the mean in a normal distribution, and according to central limit theorem, the sample sums tend towards a normal distribution. The 25th percentile, inverse normal, 0.25, 200, because that's our mean. Standard deviation is 5. There's our answer. 75th percentile, again, inverse normal, 0.75, 200 is our mean, 5 is our standard deviation, mean, standard deviation, calculator says 203.37. Find the probability that a sexual assault occurs on average between those times. So there's a very key word in here. So our key word in here is on average. So on average means we're using the means. So which means our mean gets to stay the same. This guy, though, our standard deviation now is, oops, sorry, that's supposed to be an n. Standard deviation divided by square root of n. So because we're doing means, mean gets to stay the same, so it stays at 2. But our standard deviation is now our old standard deviation divided by the square root of our mean. So 0.5 divided by square root of 100. That is 0.05. Okay, plug in the calculator to get that guy. We don't need that. Okay, IQR. Find the IQR for the sum of the sample times. So, keyword here, sums. Sums, mean, goes to n times the mean. Standard deviation goes to square root of n times the old standard deviation. Okay, because we're in sums. IQR is the 75th percentile minus the 25th percentile. So way back in a couple examples ago, we found that the 75th percentile was this, using inverse normal 0.75 and the new mean and the new standard deviation minus the 25th percentile, which we found was 196.63 equals 6.74. Alright, that is it. If you guys have any questions, please just ask.